Welcome back. Let's talk about the chemical equation. So a chemical equation is what we are going to use to represent a chemical reaction that is taking place. We have an example shown here of the combustion of methane. So methane reacts with oxygen gas to form CO2 and water. Anytime we have a chemical reaction like this, every chemical equation is going to have certain components. It doesn't matter what reaction it is that we're looking at, it doesn't matter what molecules are involved. Every chemical equation is going to have reactants, so things that are coming together to perform some kind of chemical reaction. It doesn't have to be more than one thing. You could have just a single reactant, but you have to have at least one thing as a reactant. You have to have an arrow which shows the direction that the reaction is moving in. This is sometimes called the reaction coordinate, I believe, but it's not something that's super important to us at this point. Every reaction is also going to have products, something that is formed, something that is made from the reactants. And lastly, but not least important by any means, every chemical equation is going to have coefficients. These show the number of each molecule that is involved in the reaction. So in this particular reaction down here, again, this is the combustion of methane, there's something wrong. There's something wrong with the reaction. If we look at the stuff that's involved, on the left side of the reaction here, on the reactant side, we have one carbon. We have, on the right side, one carbon. That doesn't seem too unusual. If we look at the oxygens, on the left side of the equation, we have two oxygens. On the right side of the equation, we have 3 oxygens. I know that looks like 20 and 30. Sorry, it's hard to differentiate between my O's and my zeros. But we have 2 oxygens here, 3 oxygens here. For the same reason here, we have 4 hydrogens on the left and only 2 on the right. In our chemical reaction, we are just creating matter from nothing somehow. We started with only 2 oxygens and we ended with 3. We have created matter. We are not allowed to play God with chemistry. We cannot just say, there shall be an extra oxygen atom, and poof, there is an extra oxygen atom. This is what we call an unbalanced chemical equation. It is not balanced because there are not equal amounts of atoms on both sides. And by equal amounts, I don't just mean the total number of atoms. I mean the total number and kind of atoms. We have to have the same number of each individual element on each side of the chemical reaction. Otherwise, we are lying, because you can't create or destroy matter with a chemical reaction. It's not possible. So if we have 2 oxygen atoms on the left side, we better darn well have 2 oxygen atoms on the right side, and only 2. Otherwise, we need to do something to fix that. And what we can do to fix it is balance the equation. So while we can't go into these molecules here and say, well, I have 3 oxygens on the right, I'll just say I don't have O2, I have O3. That is not okay. That means what you're saying there is that you don't have methane reacting with oxygen gas, you have methane reacting with ozone. O3 is not just oxygen with an extra oxygen. O3 is ozone. That is a completely different molecule with completely different chemistry. So instead of messing with the subscripts, what we are going to do is we are going to mess with the coefficients. We're going to put numbers in front, because right now all of these just have 1 in front of it. We're going to put something other than 1 in front of some of these in order to get the number of atoms on both sides to be the same. Now we can change the number of coefficients, no problem. Because remember, changing the coefficient, changing that number in front, you're not changing the actual molecule, you're changing the number of molecules. So I would never say, for example here, that, let's just say for the sake of example, that I need 4 oxygens here, which actually I do. If I wanted to balance this, I could put a 2 here and a 2 here, and I believe that would get everything balanced, because I would have 4 hydrogens, 2, 4, yeah. So that would give me a balanced chemical equation. So saying that I have 2 O2s is completely fine. Saying that I have 2 molecules of O2, that is completely fine, and it is completely different than saying I have O4. 2 O2s is 2 of these. O4 is some strange molecule with 4 oxygens connected together that does not exist. That would be the most unstable oxygen or most unstable molecule in existence, pretty much. That would be a very, very bad molecule. I do not want to be anywhere near that. So these are 2 very, very different things. And we want to use the coefficients to get those extra atoms, not subscripts. Subscripts change the molecule. Coefficients change the number of the molecules. So, when we're balancing these equations, we're going to have a 4-step process here we're going to use to get these things to balance. The first thing we're going to do is write the skeletal structure, which is just to say write the base molecules, the stuff that we know is reacting, write in the reactants, write in the products, with no coefficients to start with, just the molecules themselves. Number 2, balance the elements that only appear in one compound on each side, balancing the metals before the nonmetals. So if we have, for example, calcium in one molecule on the left and calcium in only one molecule on the right, we're going to balance that calcium first before we would balance, for example, the hydrogen that is in 2 different molecules on the left and 1 molecule on the right. Because there's 3 different places that have hydrogen, there's more than one way to get it to balance. If we only have 1 molecule on the left and right with calcium, there's only one possible way to get that to balance. And so we're just going to go ahead and do that first because we know it has to be done a certain way. There's no questioning whether what those numbers need to be. Number 3, elements that occur as free elements on either side are balanced last. So if, for example, we have just iron as one of the reactants, like not bonded to anything, not iron oxide, just iron, we're going to leave that till the very end because we can do whatever we want to this iron without affecting anything else. That's the thing that normally gets us. If we have something like water and we need 2 more hydrogens but everything else is balanced, well, if we put a 2 in front of the water, yes, we'll get our extra 2 hydrogens that we needed, but that 2 is also applied to the oxygen. And so we're going to get an extra oxygen, and that will then throw off our oxygen balance. So if we have something like this, where adding coefficients to the iron has no effect on anything else, we're going to save that for the last. We're going to balance everything else before we do that, because this is essentially the easiest to get balanced. So then the last thing here, if the balanced equation contains coefficient fractions, change these into whole numbers by the appropriate factor. So if, for example, again, we'll just use water here, if we had to use 1.5 to get the correct number of hydrogens. Maybe we had 2 hydrogens and we needed 3. So having just 1 water gave us 2 hydrogens, but to get our equation to balance, we needed 3 hydrogens. So we did 1.5, because 1.5 times 2 is 3. We're not allowed to keep those fractions in our balanced chemical equation, because we can't have half of a molecule of water. We can use the fractions just to get everything to balance. That's fine. But when we actually write down our true and final balanced chemical equation, we need to multiply through to get rid of those fractions. So if we had a half somewhere in our chemical equation, we would multiply everything by 2. Not just this. We would multiply everything by 2. So this would end up being 3 H2O. But the same thing would be done to everything else in the chemical reaction. Because if you just do it to the water, well then now you're not balanced again. But if you multiply everything by 2, then you still keep your balance. Alright, let's do a couple examples here. So we're going to do example 7.2 and 7.3. So we'll do 7.2 here. Let me open up my book real quick so I can see what those are. Okay, 7.2. Oh yes, this will be a nice easy one to get us started. So this asks us to write the balanced equation for the reaction between solid silicon dioxide and solid carbon. So we have silicon dioxide, and that is reacting with carbon, and that produces silicon carbide and carbon monoxide gas. Now, if you have your book and you're reading along with me, you might notice that they include the phases for these, which I don't think we've talked about yet. But if you see the little S and S and S and then G, those are just indicating the phase of the material. So a little sub with an S in parentheses, that means solid. A G in parentheses, that means gas. If you have an L in parentheses, that is liquid. And a Q, which we'll talk about a good bit later in this chapter, that means aqueous, which some people pronounce aqueous, but I'm pretty sure aqueous is the correct way to pronounce it. But I won't hold it against you if you want to call it aqueous. That means that it is dissolved in water. So the phases are actually completely irrelevant to balancing the equation. I just wanted to mention it because I believe this is the first time that it's brought up. So for us to balance this, what we're going to do is we're going to follow our rules here. We already have our skeletal structure written out. And actually, I want you to follow the rules here. So I want you to go through the steps here, see if you can balance this chemical equation. It should not be too hard. This is a pretty simple example. So work through the steps and try to balance this equation. And just pause the video and do that, and come back when you think you've got it worked out. And by the way I would suggest to check, I always, when I am balancing equations, I have little spots to write down exactly how many of every element I have on each side. So you're starting with 1 silicon, 2 oxygens, and 1 carbon on the left, 1 silicon, 1 oxygen, 1 carbon on the right. So see if you can balance that equation. So pause the video now. Alright, if we're following the rules here, it says to balance the elements that only appear in one compound on each side, balancing the metals before the nonmetals. The silicon is not technically a metal. It is a metalloid, but it actually starts out balanced, so we don't have to worry about that. The only thing that we don't have balanced is the oxygen. So if we check here, we have 2 oxygens on the left, 1 oxygen on the right. There's technically actually 2 different ways you could get the oxygen to balance. We could put a 2 here. That would get our oxygens to balance. Or alternatively, we could put a half here. If I can avoid using fractions, though, I do. I avoid using them. So I'm going to go ahead and use the 2. So that is going to give me 2 oxygens, but I also will have 2 carbons now. However, that's an easy fix. So that threw my carbon off balance, but I have pure carbon here, so I can put a 2 there, and now it's balanced. Silicon is balanced, oxygen is balanced, carbon is balanced. Oh, nope, sorry. This is why you need to be very careful when you're reading and not make videos at 11 o'clock at night, apparently, because I miscounted my carbons. There are 3 carbons there, so I actually need 3 here. But again, that's still not, since we have, anytime you have a free element like that, it tends to be very easy to balance, because again, you don't have to worry about messing up the number of one thing with something else. So we had 3 carbons there, not 2. So that, by the way, I know it's slightly embarrassing for me, but I'm going to leave it in the video so you can see that even someone that's been doing this, I've even done this exact problem probably a dozen times before, and you misread things. That is by far the most common mistake on balancing equations, is you get in a hurry and you think that you read it correctly and you didn't actually read it correctly. That is, again, by far the most common mistake, is just misreading the equation. I'm glad I caught it before I moved on. Otherwise, I'd be getting emails from you all being like, what? So that is double check again. 1 silicon, 2 oxygens, 2 oxygens, 3 carbons, 1, 2, 3 carbons. Okay. Whew. And after I got done saying it was an easy one, I make a mistake. That'll teach me to say that. Okay, let's move on to 7.3. There we go, 7.3. So this one's going to be a little bit tougher, but it's still not terrible. If you follow the rules, you will get the right answer, and if you read the molecules correctly. So this is going to be the combustion of octane. So octane is C8H18. And anytime we're combusting something, it's going to react with oxygen gas. And not only that, it is going to make CO2 and H2O as the products. Anytime we burn a hydrocarbon, those are going to be our 2 products, ideally. Now, in reality, we can actually make other stuff, especially if we have very little oxygen. You can make CO instead of CO2, which is really bad. And if you have impurities in the octane, then you can make other stuff, but we're taking the idealized situation here. So, if we follow our rules, we have our skeletal structure written here. The rules say that we need to balance everything that only occurs in one molecule on each side. Balance those first. The oxygen occurs in 3 different places, so we don't want to do that. The hydrogen only occurs in 2 places. It's only in the water and in the octane. But the same is also true for the carbon. And I'll just tell you now, in general, it's better to save the oxygen and the hydrogen for last. I say that, advisedly, because sometimes that's not the case, but usually it is the case. that you want to save the oxygen and hydrogen for last. So let's balance the carbon first. And actually, I'm jumping straight in here. I would like you to give this one a shot before I show you how it's done. Because who knows, after that last one, you might do it better than I do. So we have carbon, hydrogen, and oxygen. And our starting point here, if I can count correctly, we have 8 carbons, 18 hydrogens, and 2 oxygens on the left. We have 1 carbon, 2 hydrogens, and 3 oxygens on the right. So that is our starting numbers. So go ahead and use those rules to try and balance this equation. So pause the video now and give that a try. Okay. So, like I said, I'm going to go ahead and balance the carbons first. And I'm going to do that by putting 8 here. Because remember, we can put as many coefficients in as we want. We are not allowed to change the subscripts, though. Only the coefficients can be changed. So if I put an 8 here, that is going to give me 8 carbons. But it's also going to give me a bunch more oxygens. Because now I have 8 times 2, which is 16, plus 1. So 17 oxygens. So that's a lot of oxygens, but don't worry. We're okay. We're still okay. So we've balanced our carbon. The next thing, again, we're going to do the stuff that only shows up in one place first. So that would be the hydrogen. We're not doing the oxygen yet. Partially because the oxygen shows up in 3 different places, but also because we have this O2 here, which we can use to get as many oxygens as we need on the left side without messing with hydrogen and carbon. So that's going to be really handy. So to get the hydrogens to balance, I have 18 on the left, only 2 on the right, but I can get 18 with a 9. So 9 times 2 will give me 18. But once again, by putting that 9 in here, I'm not just changing the hydrogen, I'm also changing the oxygen. So I'm going to have 8 times 2, which is 16, plus 9, which is 25. So 25 oxygens on the right. That is the only thing that is not balanced at this point. The carbon is balanced, hydrogen is balanced, oxygen is not balanced. I only have 2 on the left, but if I put 12.5 as my coefficient for oxygen, 12 times 2 is 24. Half of O2 is O, single oxygen. So that would be 24 plus 1 is 25. So that is a balanced chemical reaction. However, what's not allowed? Hopefully you said fractions, or maybe thought fractions. Fractions are not allowed. So even though this is technically balanced, we can't have half of an O2. And so what we're going to do is I'm going to get out my eraser here, get rid of that 12.5, 8 and 9, and write in 2, 25, 16, and 18. And that is going to double everything. Because again, I have to get rid of that half. And to get rid of the half, I multiply the entire equation by 2. It's just like a mathematical equation. As long as you multiply everything by 2, you're not changing any of the equalities that exist. Except now we're going to have 16 of these, 26 of those, 50 of these, and then once again 16, 26, and 50. Well, ran out of space there. You get the idea, 50. So, that is a big balancing problem. Some of you are probably freaking out a little bit right now, like, holy cow. We had a coefficient of 25. I didn't even know that was possible, to have a coefficient of 25. This is nuts. You just tell you right now, this is as hard as it gets. For this class, anyway. In other classes, it would get harder, but in this class, if you can do this, you can do anything I would throw at you. This is the absolute most difficult that I would ever do, would be something like this, where you have lots of coefficients and fractions that you have to multiply through to get rid of. The majority of them are somewhere in between this one and this one. So we had kind of the more simple one here and the lots of stuff going on here. We kind of had the two extremes here. Most of them are going to be somewhere in the middle. Maybe where you have a fraction, but it's mostly small coefficients that you're dealing with, or something where there's no fractions, but you still do have everything with a non-zero coefficient or something like that. There are lots and lots of practice problems that you can find online for balancing equations. I would even say use the in your book. If you go to the e-version of the book, you can find like links to practice problems and stuff that you can do. There's lots and lots of things you can look at to get some practice on these. So that is all I want to talk about here for this video. It's a pretty long video, but balancing equations is a important topic, and I didn't want to chop it up into multiple videos. So in the next one, we're going to talk about a not completely different topic, but very different topic, which is aqueous solutions and solubility. So I'll see you in the next video.